ME204, Particle Kinetics using non-conservative work. We've talked about the energy of a particle, including kinetic energy and potential energy due to gravity and springs, and what those parts mean. We've also put those together in our energy equation. We've defined work, that work is a product of an applied force for a known distance, or work equals force times a change in position, or if we have a changing force, work is the integral of the force with respect to position. Now let's put everything together, including our non-conservative work. We talked about a financial account balance equation. If we have an initial balance and we add deposits or make withdrawals, we end up with a final balance. The same is true for our energy equation. Our initial energy plus or minus non-conservative work equals our final energy. Initial energy consists of kinetic energy and potential energy. Non-conservative work changes the energy in the system. It either puts energy into the system or takes energy away from the system from outside sources. And then we are left with a new energy balance, our final kinetic energy plus our final potential energy. Putting in the terms that we know, we get this equation to represent work and energy. Note that in the case of non-conservative work, we include the term plus or minus the integral of the force with respect to position. This term represents our non-conservative work. It's energy added to the system or energy lost from the system that is not conserved. Here's an example. Let's find out how fast block A is traveling after it's fallen 2 feet from rest. The weight of block A is 15 pounds, the weight of block B is 5 pounds, and our coefficient of kinetic friction is 0.3. We'll start with our energy balance equation. The initial energy plus or minus non-conservative work is equal to the final energy. If we write out the full equation with all of the terms that we need, we'll have our 1/2 mass times velocity squared plus 1/2 our spring constant times displacement squared plus our mass times gravity times the initial height plus or minus our non-conservative work, which in this case would be the integral of the force with respect to position, is equal to 1/2 mass times the velocity squared plus 1/2 our spring constant times our final displacement squared plus our mass times gravity times our final height. There are no springs in this problem, so we can eliminate the terms that include the spring constant. Also, this problem starts from rest, so we can eliminate the kinetic energy term from the left side of the equation. Note that we have two masses in this problem, so for the terms that are left, we have to consider both masses with each term. Do we have a mass times gravity times height for B and a mass times gravity times height for A? So writing the equation, for both masses and all of the terms, we have mass times gravity times the initial height of A plus mass times gravity times the initial height of B minus our non-conservative work, which in this case is the friction between the block B and the ground. It's the only external force on the system that has a force times distance. So we're taking energy away from the system, thus our work is negative. It's also a force that's acting opposite the direction of the displacement. In this case, we have kinetic friction, our mu sub k, coefficient of kinetic friction, times our normal force, times the distance that that force is applied. This would all equal the final energy state that we have, which includes our mass times gravity times the final height of A, plus the mass times the gravity times the final height of B, plus 1/2 the mass times the final velocity of A squared, plus 1/2 the mass times the final velocity of B squared. Now block B doesn't change height, so we can eliminate the potential energy term from both sides of the equation for block B. If we put the datum for A at the bottom of the 2 feet, then we know that at the end of the problem, A will be at the bottom of the 2 feet, and so its final height will be 0, which eliminates the potential energy term on the right side of the equation for block A. We also know that our length of the cable for our pulley system is equal to the length of B plus 2 times the length of A when we're looking at the lengths that will change with time. Taking the first derivative of this with respect to position, we get that the change in position of B plus 2 times the change in position of A is equal to 0. Using this and filling in our values for our equation, we get the mass times gravity, or the weight, of A, which is 15 pounds, times its initial height, which is 2 feet, minus our friction for block B, which is 0.3 times our normal force, which is 5 pounds, times the distance that is applied, which would be 4 feet. That 4 feet comes from the fact that 2 times the change in position of A would be equal to the change in position of B. If A drops 2 feet, B changes position by 4 feet. That's the distance that friction force is applied. All of that will be equal to 1/2 the mass of A, which is 15 pounds divided by 32.2 feet per second squared, times the final velocity of A squared, plus 1/2 the mass of B, which is 5 pounds divided by 32.2 feet per second squared, times the velocity of b squared. We still have two unknowns, so if we take the derivative of our change in position equation, we get a relationship between the velocity of a and the velocity of b. We're looking for the velocity of a, so our velocity of a is equal to 1/2 the velocity of b, or the velocity of b is equal to twice the velocity of a. So where we have the velocity of b, we'll substitute in 2 times the velocity of a. Now we have one equation with one unknown. Solving for the velocity of a, we get that the velocity of a is 6.65 feet per second. Our next topic is power and efficiency.